So one of the big interactions that we deal with in physics is gravity, or the gravitational force, rather. In this screencast, what we're going to do, or in this video, rather, we're going to talk a little bit about the local gravitational force. So let me give you a sense of that just for a sec. So let's say you're standing up on the second floor of a building, and you have a watermelon or a bowling ball, because why wouldn't you take one up there? And you drop it down. As it turns out, we observe when this thing falls down that it changes its velocity at a rate of 9.8 meters per second squared. This is an empirical fact. We just observe this. Now, as it turns out, if you go to different places, it changes a little bit, but it's pretty close to 9.8 meters per second squared almost everywhere. So this has a really special name for us. It is the acceleration due to gravity. We give it a little g, and it is equal to plus 9.8 meters per second squared. Now, if we're actually going to do something with it, we have to understand that it acts downward. And so we have to put in a coordinate system, which is typical to put in a coordinate system where we measure the y direction upward from the ground. And if that's the case, then we have a vector acceleration that's given by 0 minus 9.8, 0 meters per second squared. This is the acceleration due to gravity in its vector form, described when you choose the positive y direction to be up. So you have to be careful there, because you can sometimes choose it to be down. Maybe it's useful to do that. Okay? What this does, it helps us to understand this from a force perspective, because now we can understand what the force due to gravity is if we work with the momentum principle, which is, again, this really big idea in physics. What it does is it tells us how the momentum will change with time in response to net forces. So if we have a situation where the only force that we're interested in is the force due to the Earth, like I've started to draw here, then we might think of that net force as just being the force due to the Earth. So we're neglecting things like air resistance or wind or any of these other sorts of situations. What this will allow us to do is then figure out what is this force due to the Earth. So we'll take the momentum side and we'll break that out just a touch, and we'll say that's the mass times the change in the velocity with respect to time. And the observational fact is that that is always 9.8 meters per second down. So this is precisely m times g. So the local gravitational force near the surface of the Earth is the mass of the object times the gravitational acceleration. Now this is really cool, because we can use this to make some predictions about situations where we neglect any other force except for the force of the Earth. So that's what I have over here. This is our vector description of the position update and velocity update. What we're doing now is we're going to say, well, that net force is equal to the force due to the Earth, which is m times g. Well, in all of these situations, the acceleration piece, which appears here, is always equal to the net force divided by the mass of the object. Well, for us, that's going to be m times g divided by m, which is simply the gravitational acceleration. What we're going to have now is a set of equations that we'll call kinematic equations. The reason that they're called kinematic is because they don't deal with any of the dynamics. They don't deal with any of the relationship between the force and momentum, at least not directly. These might be equations that you've seen before in some of your maybe earlier physics classes or physical science classes. But here we've written them in a vector form. So this is the position one, and here is the velocity one. Okay? So all of these, both of these equations just depend on kinematic quantities, things like position, velocity, and acceleration. These are very, very useful for predicting motion when the net force can be approximated to be just the force due to the Earth. Okay? On the, oops, missed some vector signs here. On the notes, what you'll see is actually this broken out by components where we've chosen a particular y direction. And those you might actually be more familiar with, because these become 4 scalar equations, 2 for x and 2 for y.